Please welcome the Vice President of Biological Technology and Research at BIOS Lighting, Robert Zola.
Thank you. Thank you. All right. Yeah, so thanks. I'll try to keep it quick, but I have a lot of really fun stuff that I get really excited about, so bear with me. All right, so the topic is, to what extent can electric light simulate daylight? So some things about me and why I'm here. So I came from the Lighting Research Center, and after that I went to NASA, and I helped put the first light on International Space Station. Subsequent to that, I was the subject matter expert for the circadian lighting on International Space Station. And so, Space Station is interesting for a lot of reasons. But from a circadian standpoint, it orbits the Earth every 90 minutes, which means it sees a sunrise every 90 minutes. And our biology does not know how to handle that kind of information. And so what we did was we took basically the underlying principles that we know about what circadian biology is looking for, so that we could create a spectral solution. And so this is something that we did in 2009. And 8 short years later, it actually turned into please play. Well, it's a really cool floating light on International Space Station. Anyways, I'll talk about it. And so after that, I was jet lag mitigation expert for the Dodgers, the Olympic ski and snowboard team. I'm now advisor to the International Well Building Institute. I'm a National Science Foundation fellow for my time at the Center for Circadian Biology. And so long story short in all this is I'm a total nerd when it comes to circadian stuff. I'm not really a sales and marketing guy. I'm like really passionate about this stuff. So I usually like to share everything that I know with everyone that I talk to. All right. So I'm here to talk about circadian rhythms, and it's a really important thing, and it's really underlines a lot of things that are critical to our health. So in 2017, the Nobel Prize in Physiology was awarded to the people who discovered the mechanisms of circadian rhythms. And so what we understand is that our circadian rhythms is a pervasive part of all biology, not just us, but every organism in our ecology has a circadian rhythm, which means that it has an internal clock dictating when it does specific things. So within us, every cell in our body has its own clock. Our gene expression is 43% of our gene expression is circadian, which means that we have peak activities of something happening at the same time every day. So the idea about this and why it all makes sense is it's really about strategic timing of resources. So we utilize hormones at different times of day. It doesn't make any sense for our bodies to produce a hormone at a time that we're not going to use it. Things like our metabolism is gearing up at times that we're supposed to anticipate food. Even from a behavioral standpoint, our resources, not so much us, but people who require time of day for safety, for food, we strategize everything in our biology, in our ecology, in our surroundings based on time of day for survival. And so if you think about us, we're really complicated, and it really takes a lot of things to line up in sequence in order for us to be as efficient, as productive as we possibly can be. And so light's role in all this has been predicated upon the fact that we've discovered in 2001 that there's another photoreceptor in our eye that we didn't know existed before 2001. And it goes to a different part of the brain that regulates our circadian rhythms, and those outputs are things like our physiology and our behavior. And so what this does is it basically showcases a evolutionary relationship that we've had with the sun. We use that sun as our synchronization tool. That's our primary key, right? So temperature can change very, very wildly from day to day, but that sun will show up at the same time each day, and it'll go down at the same time each day within seconds from what happened the day before. And so we use that as our primary synchronization tool. But now we spend all our time indoors, and so we've broken this relationship, and so there are things that happen. And so the consequences, basically, I'll sum it up because for time, I'll just give you the nutshell of what it is. So basically, under natural dark cycles, so a bright day, dark night, we go to bed about a couple hours after the sun goes down, and then we wake up right around when the sun rises. Well, now in modern society, we spend our days in spaces that are not bright enough, and then we spend our nights in places that are not dark enough. So it's neither bright enough nor dark enough in this environment. So this actually causes a shift, a behavioral shift. So now we go to bed much later than we should, and we wake up significantly after when the sun rises, or at least it's when we want to wake up, if you will. So it leads to more night owl tendencies. So to get into what this feels like, okay, I don't even know if I have time for this, but so basically what happens is we have this sleep pressure that builds up over the course of the day, and then we have an opportunity to sleep, and then that sleep pressure dissipates. We wake up and it builds up again. And so this is all driven by sleep timing. And so what combats this sleep pressure is a circadian drive. So these upward alerting signals are basically combating that sleep pressure. And so within this profile, there are things you could actually identify with. So we have this inflection point, which is known as the afternoon lull. It's that feeling you have, this is what 5-hour energy totally capitalizes on. It's that feeling you have after lunch. It doesn't matter what you ate. It just happens there. And so after this afternoon lull is probably the coolest thing about circadian rhythms that nobody talks about. But this is this burst of energy called the wake maintenance zone. And so what this is an actual survival mechanism that we've inherited from our ancestors, really for survival. If you think about it, before electric lighting, the onset of darkness was a really scary time for us. It was when we went from predator to being prey. And so it was really important at the end of the day to get our stuff done, go find safety, and survive the night to make it to the next day. And so what we find is we actually have this burst of energy. It's not just physiological energy, it's neurobiological energy too. We're actually smarter, more creative at this time. And it's all designed, get our stuff done, go find safety, and survive the night. Then after this subsides, then starts the opening of the sleep gate. A hormone, melatonin, is produced. Basically what happens is our heart rate starts slowing down, our muscles start relaxing, our immune system starts boosting up, our metabolism shuts down. And so we prepare the process of sleep. And then they pick back up here with something called our cortisol awakening response. And so this is basically designed, if you wake up every morning at the same time without an alarm clock, you could thank that cortisol awakening response for getting you up at the same time each day. And so these are things that we don't really recognize as happening, but it all happens underlining. And so this is fundamentally different because it's all driven by light timing. So it basically uses the sun to figure out when all these things should happen. Now, if you're a night owl, what happens is basically this rhythm gets shifted later. And that really cool survival process that you have encroaches the time that you know you should go to sleep, but you can't go to sleep. You're wide awake and you have no idea why. And so basically what happens is you can't sleep during this time, and of course society requires you to wake up at a very specific time, and what time is that? That is the time that you literally hate life, and you do not want to go anywhere but your bed. It is the time that you are doing nothing productive at this time. So what do? We reach for, coffee, Red Bull, food to try to get us going to basically keep up with the Joneses and do what we need to do. And so the common strategy amongst night owls is basically this. You just suck it up. During the week, you just deal with it, and on the weekends, then you could sleep in and recover from all the sleep you lost throughout the week. And so there's this wide variation of sleep timing. Well, this is actually a big problem because what we've learned is that this higher variance in sleep timing is the best predictor of poor academic performance. We've also noticed that if you give people who have this night owlism brighter light during the daytime to shift them, one, they become less of night owls, but two, their ADHD symptoms are reduced. So what we're starting to see is that these behavioral outcomes that are downstream consequences of circadian disruption are more prevalent in today's society. ADHD is more prevalent in today than it was much earlier. Eating closer to circadian night is associated with significant weight gain. So even though, if you're eating at this time, your metabolism is shut off, your body's like, dude, we're supposed to be sleeping right now. I don't know what to do with this stuff. So it leads to these problems with our metabolism. All right, and so there are all sorts of problems that are associated, that are downstream consequences. This came out of the Salk Institute of circadian disruption and disease. So we see things like ADHD, so as we age, autism, bipolar disorder, all the way up to cancers, Alzheimer's, obesities, childhood obesities, fatigue. So they're insufficient sleep, fragmented sleep, insomnia. So all these things are downstream consequences. All these things are more prevalent in today's society. So this is something that's not, this isn't this weird thing that people are talking about. This is real. This is something that's prevalent, and if in the 30 seconds you got from what night owlism is, I'm sure there's a lot of people, I saw a lot of heads nodding in that. This is something that is real and pervasive in our society. All right, so I'll give you 2 seconds of what it is. So there's a special photoreceptor that drives this. I won't go into too many details, but it contains melanopsin, and it's most sensitive to a sky blue color. That's really exciting. I won't go into any more detail than that because I got a pretty graph that kind of that shows this a little bit better. All right, so also what we understand is that we actually, in our skin, have an optical window that allows far reds to penetrate deeper, and we have another photoreceptor in the skin in the mitochondria, which is pretty cool. What I'm really excited about is that just in the last 6 months, we discovered that there's another photoreceptor that is a twilight-specific photoreceptor that really talks about the importance of twilight. All right, so when you break down the impacts of different wavelengths, so this is what it looks like outdoors, and it's really beautiful and all that. And this is the spectral power distribution of what is comprising that outdoor environment, a very broad spectrum. And so the end of day of Q is kind of in the violets. There's a damage potential that's in kind of the short wavelength blues. The circadian response is over here in the sky blues. Visual efficiency, lumens per watt, and everything is over here in the greens. And then there's a healing and energy potential with that skin optical window side of things that's there. So this is kind of, you see, in daylight, you get pretty much everything, and as you get more Rayleigh scattering, as Star mentioned before, you get more energy in the end of day of Q, which is really cool because it's exactly how our nature has told us how to do things. Now, if you take that and think about the built environment and provide, say, you want that daylight LED that Star was talking about before, well, the spectral power distribution looks like this. So it has, some damage potential. It has everything's pretty much in the visual efficiency because that's all they care about is lumens per watt. There's nothing in the circadian response. There's nothing in the healing and energy, and there's nothing really going on for that end of day Q. Now, what we do at BIOS is we basically said, well, that's not right. We should basically reappropriate all the energy in the circadian response standpoint, put a lot of energy in the far reds because we both think those things are important, limit how much energy is going in this region, and still make sure that it's a nice bright white light. Now, I would love to say that I'm done talking here, and I know that the people who are giving me moderating time would say that too, but I don't think that that's all that's the whole solution. Because what we know is that there's a difference between what's going on in an overcast day versus a bright sunny day. Now, Star mentioned that there's maybe a 10x difference in brightness, but there's something interesting that happens here. So from a spectral power distribution standpoint, those clouds are nothing more than puffy white diffusers, which are just scattering light. So the spectral power distribution is the same. So I think there's actually something more that we need to be doing. So if we really replicated the spectrum of daylight inside, we could never do better than an overcast day. And there's something actually phenomenal about that color separation that we believe is psychologically important. Now, of course, if you have a window and that window has no view of the sky, as Star mentioned before, you're not getting that color separation. So it's still something to consider. The windows are great, but they don't do everything for you. And so what we've created is actually something that has this color separation technology. I know we're pressed on time. I have a little bit of a demo to do it, but we also did a really cool Earth-Mars daylight experience room at the Wings of Eagle Discovery Center in Elmira. And so basically what we do is replicate to kids what it looks like, what a sunrise and sunset looks like here on Earth, and then juxtapose against what that would look like on Mars, where the sky gets redder and the sun gets bluer. And so it's a really cool demo to see that. And so basically what happens when you do this in a sky response, basically you want high amounts, you want to provide that blue sky signal, high amounts of that circadian response, a lot of the red still in there. And then as you go to twilight, you want to amplify more of this end of day Q, which is really important for basically telling our body, all right, this is the real end of day. All right, so there are concluding points. Light can provide right biological cues. What we do, didn't want to be too much of a marketing pitch, but we provide these key biological wavelengths in the built environment. So we take a biology-first approach. We don't do anything unless there's a biological mechanism for what we do. So color separation creates this really cool holistic approach. And then it provides critical time cues that are essential for health. Hopefully in the short time I had to talk, you got that gist. And then what we try to do is we try to simplify the controls so it doesn't take a supercomputer in order to create this system inside. And that dramatically reduces the cost and increases compliance, which is really what we're about. And of course, Star kind of mentioned this before, but there are a lot of things and there are a lot of areas where we need this energy to come from. And so the window only penetrates so far, and if you're outside of that window, you might not be getting the exposure you think. You might not getting the sun views you want. So if you want it to penetrate the space, you got to make sure that it truly penetrates the space and is where those people are. And I'm done. That's it. Thanks for your attention.